Today we're gonna continue on uh, building some collision checking. I've been spending the day looking into GJK and different algorithms, and I have implemented a working GJK algorithm. Um, yeah, since I was trying to solve the problems that arose when using the SAT. This algorithm has the problem that it detects a collision when the axis of the two bounding volumes are parallel. I could fix it, but I instead wanted to do a rewrite of the whole thing. So yeah, today I'm gonna spend some time on that. Let's see, we will simply create a new set of files for this, since we might be using the separating axis test in a different implementation. Yeah, so we will do this. I'll not talk too much in terms of the actual function here. Let's do a inline function that goes static inline, actually, maybe. Now let's start out with a basic function that is not static. We will have a function overlap axis, and we will have yeah, we will do some stuff here. We'll take the G vector axis, and it will be a const vector reference axis, of course. And one thing we need is a squared size of the axis. And if it's lower than a certain threshold, we are separated. Well, maybe we don't want a constant, because we will normalize the axis. Let's see. Uh, uh, so we will want to calculate the penetration here. Let's see, the rotary radius A is going to be um, let's do this for A. Yeah, we used to calculate the rotation here. Let's see, inside this function. Yeah, so let's just do it somewhat simple. Right here we will take the bounding OBB reference box 1, and we will take the bounding box WC box 2, and it's the reference. Yeah, great stuff. So we will project the radius onto for the first one onto the axis, and this will be a sum of box 1 half widths and the first component, the x component, times the absolute value of the dot product of the axis and the box 1 x-axis. Let's see our parentheses here. And of course we need to grab the actual dot product. Then we do a plus and do the same. Oh, wait a minute, let's do it on the same line, yeah. And then we do a plus where we add the y translated by the y-axis. And then we add the dot product of the z-axis, or rather the z half-widths. Let's see, no pun intended. We do it for, oh my god. We do it for the z-axis. Yeah, and we would like a radius b to be yeah, since this is not actually rotated, we'd expect the dot, we simply add up wait a minute, no. So we of course want to translate box 2 half widths, and maybe we want, and we of course want to translate by the different axes. Let's see, oh my god. So if I do like this, I can specify the x-axis like this, and I can specify the y-axis and the z-axis, because it's going to be a B, B, and therefore we do the transforms, we do a vector called to send diff centers, and we let's see, we subtract the position of box 2, box 2 center from and we subtract box center 1, and we then center distance is equal to first of all the absolute value of our math vector dot product here between the difference between the centers and the axis. Let's do it in the other order, just to do it as per usual. We grab the first value of the dot product, And then we have a um, a value called penetration, where we take the radiuses, actually called radii, and we subtract the center distances. And if positive, we have a penetration. If negative, distance is found. There we go. So if the penetration is lower than 0, we simply return false. Otherwise, we return true. So this is basically part of a overlapping test. And then we actually want to include our SAT here. I mean, we're gonna redo test intersection on blah blah blah. We're gonna leave that. I think actually we're gonna move it to the SAT. Since old functions, we move it. We of course run into problems. Let's see. Let's close these since we are not using them right now. We need a major overhaul of this library, and I'm sorry for all the deprecated code. Find smallest penetration. Yeah, we will move that as well into the SAT. Simply, let's see. Whoops, did I? No, I didn't. So the old deprecated functions, they are SAT based, so I'll definitely be moving them into that part of the library since it makes more sense that they are there. But now we have a problem, as you might see. This function doesn't work anymore, and which ones do we actually call? Let's see up here. Yeah, I did some different checking. Let's remove that and stop using the GJK for now. Let's close the temporary input polling. Let's put that inside a scope. Yeah, it won't be long before I do a lot of different cleanup. I mean, everything is sort of messy. So we call this function, but we do not call this function, and therefore I will simply deprecate it for now. C. There we go. And this will also be somewhat deprecated. At least for now. Yeah. Everything will run since we're not using the new system yet. Yeah. So we would perhaps like a function where we get some information. We want a bool find contact info OBB on AABB, and we will take our or rather we will take maybe we will take only one. Yeah, so that's fine. We will then kind of iterate over the different access information. So for each axis, maybe we just want to return the penetration. Yeah, we could do that. We'd know that this kind of would. Let's see. If we return the penetration instead of checking the information, and let's see. We probably won't get around let's do negative 1.0. We could, instead of doing this calculation every time, we could just pass it in. G constant vector reference div centers and we simply calculate that. Oh, let's see, there we go. And this will work exactly the same. And we just update the method declaration. There we go. So now we can test each axis. And we can store the smallest penetration is equal to float max. And we can set the smallest penetration index unsigned int smallest pen index to be, let's see, int max. Uint max perhaps. Yeah. Great stuff, great stuff. And then we can simply call our method here. We pass in the OBB, the AABB. The axis we'll get to. We will do it in a way where we first check relative to let's see. Oh, wait a minute. Let's see. So it doesn't want. Wait a minute. I could do const here because I'm not changing anything. I'm just using it for calculations. So if I do like this, things will probably work. And then we do const. Well, G vector L axis, we're going to create a new one anyway. GC vector axis. Yeah, we of course aren't going to change the original axis. So, yeah. Anyway. If this is above 0, we can do a check. We can do a check. And if it's let's see, penetration is equal to 00f. We set penetration equal to that. And if penetration is lower than the smallest penetration, we simply do an update. Where the smallest penetration it gets set to the penetration, and the smallest penetration yeah, we could do okay, we're getting into trouble here because I want to actually not test any more axes if we have found a separating axis. So let's see. First of all, we could do if penetration is lower than 0, we simply return false. We don't need to bracket that. Then we can do a check if the penetration is lower than the smallest penetration, and then we set the smallest penetration to penetration and the smallest pen index to 0. And we simply do this for the first 3 axes. We could do it in a for loop. I'm just gonna do it verbosely here. So this is the first 3 axes. Then the next ones are going to be the x-axis of the AABB, OBB axis, AABB axis, and we do this 3 times as well, 1 time for each axis. There we go. Then we have the different 9 axes. And we can store a best best single axis is also going to be unit max. And we set the best single axis to the smallest penetration index before we continue on. Then we do the exact same thing, but inside here, we do a cross product between math cross between the first axis of the OBB and the first axis of the AABB. Next, we do the first axis of the OBB against the second axis of the AABB. Let's see. Then we do it, of course, for the last time here. Then we do it OBB axis 1. Let's see. OBB axis 2. And first we do it by the x-axis of the AABB. Then we do it on the y-axis. This, of course, needs to be updated. 9, 10. And the last one, the c-axis 11. And then the OBB axis 3. And we swap this. The y-axis and then the c-axis. There we go. And we would like to print our information here, smallest pen index. With pen smallest penetration. And best single axis. Best single axis. There we go. So this is our test. And let's see, we're just gonna run it. And we take the dynamic object and the static object here, and we simply run it through the method and see what debugging information we end up with. Yeah, so this method is better than the previous one because it detected a if the index is equal 0. Uh, yeah, we simply skip it. Yeah, I'll not code it in because I'll just end up forgetting it. And if I change the for loop, yeah, this is great. All right. This is great. So I can't recall if I actually did it during the last episode, but we did some calculations in terms of the axis indices and yeah, some different checking, which I'm gonna copy in, and we will implement it in terms of actually detecting the contact normal. As you can see here, we calculate the normal by selecting, yeah, let's do, instead of that, if the index is like that, else if the index is below 6, and then else. First we calculate the normal like this, and we ask ourselves, this is alongside this the calculated difference between the points of the centers. If not, we flip it, and let's do the same thing here instead of wait a minute. Yeah, I don't have this array. We could do a switch. Perhaps. So yeah, this means that the collision happens on the faces of the AABB. This means that the collision happens on the faces of the OBB, but yeah, this will rarely happen. Maybe we want to switch. Anyway, we could simply do an array of axes here. Yeah. And instead of using that, we will do like this. 1, 2, and then our algorithm also gets easier to change. 1. Let me see. Yeah, I'm doing this correctly, right? Yeah, first with the first axis, then the second axis, then the third axis. I should be able to see it. I just wanted to make sure. All right, there we go. Already this algorithm is better than the old one since it handles the axis way better. Let's do a definition here where we do the normal and we simply assign the value here. The normal and we can calculate the different axes of this. Let's see. And the normal is going to be like this. So the normal is going to be like this. The OBB, and then we normalize it. If the then we flip it. All right. And then we can print the contact normal. Let's see. Huh? Let's see. Does it crash? Check the overlapped axis. Oh yeah. There we go. All right, great stuff. Let's see, we're not getting any. Yeah, the contact normal is definitely not right. It has to be flipped. But yeah. We get the contact normal. Huh? Yeah, okay. Great stuff. So we end up getting the contact normal. We get some untransformed information here. I don't know why it gives a warning there. Anyway. So yeah, it basically collides with but yeah. Great stuff, great stuff. So the contact point, let's disable this. Is the ABB. For the second function, the contact point is this, that is the OBB. And this is all untransformed. Meaning that it's just in local object space. And we do the last part here. We do the OBB, ABB, the OBB, the normal, the normal. There we go. Let's see the contact normal. Let's see. Let's do a contact point that we just store and transform. Then we post the contact point. So yeah, we do get some information here. This is not complete yet, since we need to we'd actually want the transforms in terms of doing checks. Let's see, how many instructions is that? I think this is probably faster. There we go. And yeah, so we can't transform. Yeah, so in general, it would be easier if we had the transform 1 and 2 here, but this means that we have to pass in some more information, not there, but up here, I think. Yeah, let's move all of this because we do not need it. Let's see. Let's see. So yeah, I really don't like passing in the transforms, but I kinda need to do it. Maybe we just want parts of this information. Let's see if we split off some of the information. So yeah, if we store the smallest penetration, we could do another algorithm that calculates each point transformed. I mean, this uses the smallest penetration index. and the distance between the centers. So if we have a function where we pass in the smallest penetration index for this collision, we store the difference of the centers. Maybe we don't need to do that, but it would be perhaps helpful. The next one here will also use the difference, the smallest index. Yeah, I think maybe we want another method to do these calculations here. Let's move all of this out of the function because we do not need it. We also want to move this eventually. Let's see. Okay, so we want to store a vector of we want a unsigned int vector, best single axis. Then we want another unsigned int vector. Um, and we call it out. Out smallest pen index. And we lastly do a vector of floats out smallest pen. We simply redo the method. Let's see, let's move this. So if we ever get to this point, we will actually have a collision. So let's see. Are we in trouble somewhere? Yeah, of course I need to pass in the arguments, but anyway, if the smallest penetration is unlike float max, let's see. And or rather, if this is equal to float max or this is equal to uint max, we simply return false. Otherwise, we set the vectors here. We place back the single single axis. We place back the smallest pen index, and we place back the smallest penetration. There we go. And we return true. Okay. We then need to copy these vectors. Let's see. We want one of those, and one of those. And let's do it. Pass them in. If there's no collision, we will simply continue. Otherwise, we will take the static colliders and then place back the eye here. We of course do like that. Then we actually want a function where we get out this information. We want out. Yeah, we can just copy from here actually. Yeah. Yeah. And instead do out single big out. And we simply clear them. Yeah. We will actually create them frame by frame. So I don't think we need to do that. Let's see. Let's store the old one as a commented one. There we go. Then we, of course, need to store this information outside of the method. Yeah. Whoops. Oh, static colliders. We already got that. Best single axis, smallest penetration index, and the smallest penetration. All right. Then we will do this again. We will skip the floor. Yeah, so we want to calculate some let's see. We actually want something like this. We also want to calculate the transforms. Maybe we want transform static objects. And we will do some stuff here that is kind of hacky, I think. Object. And we will ask, let's see, can't we ask about, yeah, we can, but yeah, this is kind of hacky. How do we actually update the transforms for? We don't update the transforms. Which is the problem. So how do we fetch the transforms for each static object? Yeah, that's a problem. Our system doesn't support that. So the transform, texture transform, object transform. We could store the transform index inside the bounding volumes. That might not be too shabby. Yeah, I want to rename this, and I also want to store the transform ID. Yeah. Yeah, let's do that. We might want to link up to a, and we do a integer transform index. Yeah. All right. We do it like that. Let's see where. Okay, let's do it all from the top. Yeah, I've been wanting to do that for a long time, so let's just do it now that we are messing with things. It's just renaming. I mean, let's see, and then we need to go into the header file, of course. Let's see. There we go. And swap this. Also now we can just pass in a reference to our collection of transforms. Let's see. And in here we also want to change that. Okay, also in here. All right, also in the camera class, man, we ended up with a lot of different stuff that needed renaming. This is in the collision resolution. We of course have to update in here as well. Let's see. Did I not correct it? I didn't. Let's see. Bounding box. There we go. Great stuff. All right. So these are the base bounding volumes, which we are probably not using anymore. Are we? Well, maybe we're using them temporarily for construction of these things. So the temp2 transform index is going to be the object transform. That is for the static objects. Then we do the temp2 transform index is going to be the character. There we go. There we go. All right. Now we have linked it to the proper transform index, I think. Yeah, we could store it on the bounding spheres, but I don't think we need to. Anyway. So yeah, instead of actually passing all of this out of the function, we could do, let's see, I'm gonna close some of this since we're not going to use it. Yeah, so in our application here, we don't exactly need to store this outside of the collision checking anymore, although I guess we don't mind passing it out of the function. Since we just compile the information, and I mean, yeah, I'm unsure. I mean, we could pass in just a transform specifier now that we kind of changed the system and kind of save ourselves a lot of passing data around. Yeah, this would be make us able to yeah, I think we will revert this. Yeah, let's save this as a version we always can revert back to. Instead we do a vector of object transforms. Transforms. We will do that instead. We will save that. Let's see, in the SAT, we will disable this. And then we re-implement all this. Yeah. And then inside our collision checking, we do also a renaming of the, or rather, change of the signature here. Object transform, reference transforms. We will do like that, and inside here we will save that for later and do like this. And we will instead pass in the transforms here, and then simply do like that. Outside in this part of the function, we will disable this part of the code here, and we will, yeah, I think it looks more neat at least. Whether it works more neatly, and then the reference to the collider collector, collision collector. Yeah, we will of course redo the signature whenever we have some contact information to pass out. All right, we have different contact information here. All right. Then the, let's see, the contact point is going to be transformed. Vec3 multiply matrix, and we take the contact point and multiply by the transforms. The transform of the AABB and we swap it around here. And then for our last part of the function, we need to do some math. But let's just test this. Whoops. We want to do like that. Let's just do it in terms of the floor, no matter what. Okay. If I is equal to 0, we just continue. Let's see. So the contact point, well, that's not correct. I mean, yeah. We of course need to let's just we return true since this is not done implementing yet. Let's see. Well, that's not correct. The contact point is 0. Huh. That's not great. That's definitely not great. Let's see. Well, we do object, or rather update the matrix here. For some reason, the contact point is 0. How is that? What happens if we simply disable. Wait a minute. When I do the, let's just see, if I don't apply this, do I end up in a situation where everything is correct? I don't think so, but it didn't used to look this way, did it? Maybe it did. And we do a ah. Um, let's see. How do I transform the contact point, or rather the vector usually I take the half width and I do apply the transform. I mean, it should work, shouldn't it? Let's step into this part of the algorithm. All right, let's see the a transform index, and oh, the OBB doesn't have a transform index. That's not great. That's not great. Let's see. Okay, we missed that one. Let's see, did I disable the breakpoint? I think I did. Anyway. Let's try doing that. Great stuff. Great stuff. Now we actually have a nice looking point of contact. Uh, but it doesn't look right, right? I mean, it's not in objects, or rather world space, as far as I can see. It's more likely, I mean, it's definitely not in it's more something along the lines of inside whatever object we're colliding with. So yeah, that's not great. Maybe if we translate it, it's supposed to be translated by the Hmm. I mean, without this multiplication here, what do we end up with? Yeah, we're still nowhere near. Let's see. Maybe I should step into the function to see what happens. I mean, yeah, maybe I should see what happens. All right, let's do the ABB has the transform index of 2, the OBB 5, so 2. What does 20? Oh, now I know. The last component is not 1, therefore we do not get the translation. I immediately knew why. Let's do a actually this is supposed to be, let's see. Um, ah, all right. Let's do a replacement. This is going to be vector. This is going to be vec3. Hello. Yeah, I'm building the engine myself. Thank you. It takes a long time. Welcome to the channel. So mm, um, we could do a copy here where we use the modified version, and then I'm not great. I'm only okay at math. How about you? Let's just test this. Do you know vectors and matrices? okay, yeah. Yeah, sometimes you don't need a lot of math for that. I used to do web program. I used to do web programming when I started doing stuff. Yeah, it's really nice, and once you get a grip on it, it's really awesome. Let's see, do we have some? XC component. Let's see, we could do maybe a function that adds a 1 to the end of the vector. Yeah. We could do the masking, but it would be a few steps. Yeah, with physics or we could also do, yeah, we could do something along the lines of, not like that, but we could do something along the lines of this. So the vec3 here. Uh, I'm implementing physics, so I have to calculate where objects intersect, and I'm just modifying a math function to uh, handle the math a bit more elegantly. Let's see. Where did we go? We do like this. I realized that there's an error inside the uh, a part of the calculation. So yeah, I needed to fix that because yeah, the math wasn't working properly. When you multiply a vector with a matrix, if the last component of the vector isn't 1, you won't be getting what is called the translation out of the matrix multiplication. So yeah, I realized that I had that problem. So first we mask off the and then we simply just add the old modified one with the required value. I don't know assembly yet. Um, uh, the math library is sometimes implemented. Oh, I do get. Let's see. So yeah, the contact points. Okay, maybe we want to swap these back and then do another one here. Thank you. Um, yeah, but I think I solved the problem, but let's see. I'm not sure that I actually did. All right, now everything looks fine. Whoops. I prefer not to step into this function right now. Let's see. So yeah, now everything looks correctly. So the problem was exactly as I thought it was, but the the other problem is that other functions that use the same function I tried to replace work with the old one. Yeah. I'll make some different effect shaders. I already made everything here works on shaders, the lights and the texturing and everything. So yeah, doing shaders is kind of something you have to do. Let's see. I think this actually works exactly as I want it to. Yeah, so that is awesome. Yeah, so the bug was this version needs a 1 at the end, which this one adds. Yeah, so right now I'm doing calculations on how to handle the physics. Yeah, I use the Trello.com. Sometimes I use it more regularly. I actually don't know how, if I need to update it. We have done a player camera actually. Bug fixes, and we definitely haven't done that yet. Changes. No, we haven't done that yet. Rigid bodies we have done. Okay. Yeah. Uh, so this is just my basic to-do list. I sometimes forget to update it and I just start working on something. So yeah, I'm not always using it properly. Yeah, so I recently added rotations to every object, but as you can see, the green box that follows the object around doesn't turn around with the object. So I have to do a physics system where the box kind of follows the object around, and then every physics interaction is based upon how the box is oriented in space. So if it I mean, if it's like this, it's supposed to fall to the ground instead of floating in the air. But yeah, it takes a long time to implement the correct math and the correct methods, and I've been doing different stuff for a couple of days now. I'm soon there at the endpoint where I can actually uh, implement the correct physics, but as you can see here, the line that goes through the object is actually oriented the correct way. It goes from the minimum and to the maximum of the actual model. So it's kind of like a representation of the new box I'm trying to calculate and do collisions with. Yeah, anyway. So this is the player. if I swap to a free floating camera, there's a player that can jump and that can shoot. Yeah, perhaps you saw the yellow line where he kind of shoots a ray. I have it disabled it the most of the time, but let me see if I swap to his camera and just reorient it and then jump back. I should be able to shoot the model or not. Nah, it doesn't really register correctly. Oh well, maybe I need to have the player actually under control. Oh, I forgot to reload. Yeah. The rectangle you can't see or the one that you can see? Because I'm not really rendering the one that I'm interested in working with right now. I'm uncertain if you mean this green box here, or if you mean the box that we actually can't see that follows the line, a white line here. That's there is a box, but it's not rendered. Um, oh, the box that doesn't rotate? Okay, yeah, sure, I can show you that. So I have the renderer over here, and I'll find the place where. Hello, welcome to the channel. Long time no see. That sounds like you're having a good time. So, um, this is the part where I actually update the box. So I have a offset inside a memory location that holds not yet, not yet. Sadly, I'm messing around with the physics. Right now, I have to do some um, rework of the physics engine because the objects now can rotate, and the old physics system doesn't support that. So I've been doing a lot of rework on the collision checking and the um, the physics engine. I'm getting close to where I'm done. Um, so that's great. Um, but I will definitely do it once I um, get done with the physics system, because yeah, we would like a in-game level editor of sorts, and I think I would do the UI and some different text stuff inside the actual game engine. Probably something like a very, very simplified version of I'm GUI. But yeah, that will probably take a long time. Uh, the collision checking update has been taking quite some time. Let's see. So we got to a place where we have the translation of the matrices done correctly. And now we have this. So this is when a point collides with the faces of the first box, meaning the OBB box, and this is when a point of the OBB collides with the faces of the AABB, meaning our static meshes, which for now are all AABBs, and this is when an edge collides with an edge. And right now we are able to calculate the edges somewhat, but we would still want to translate them. Let's see. So to be able to do that, we would first like to actually translate the edge into world space. So we will do as with the previous parts of the calculation. And we will of course do it down here as well. Instead we will use the AABB. There we go. Yeah, I think it really helped that we moved an index for the transform inside the AABBs and OBBs. Yeah, so we calculate the edges. Then we want to calculate the actual contact point. And let's see. So how are we supposed to do that? We are supposed to take the edges and then find the contact point that is closest to one of these two line segments. Uh, and let's see. We set the axis. Actually, okay. Simply calculate the normal. We have these two indicators of what axis to use. So we kind of have a point and a direction. The separating axis gets calculated by this. Let's see, then we yeah. This is some real math. Yeah, it's pretty rough on the math department here. Yeah, yeah, yeah. Yeah, you can start at the first video. I show on YouTube, I show pretty much everything I've done. There's only a part about the depth stencil buffer that I haven't shown. So if you have the patience to live with me messing around and not always knowing how to do stuff, you can actually almost copy everything in here. But yeah, physics is really hard one to crack if you haven't done physics before, which I haven't. We at least need a dot product of the directions. Where we take the OBB axis and we pass in the axis 1 here, and then we want the ABB axis of number 2. And we of course need to grab the whatever component that has. So that's a start. We can also get a squared magnitude of the direction 1 by just doing a dot product of itself. And we do a squared magnitude of the direction for 2 as well. We could probably just do some simplification of that. Then we want to calculate the difference position between the two points on the edges, meaning that we want to subtract the point on edge 1 with point on edge 2. And then we want to know how close the difference is to each of the, or rather how aligned they are with this position is aligned with the axis of the different objects. So we need to do another dot product where we do a dot product between the axis for the 1 and then the difference in position, and do the same for number 2 here. There we go. And we can calculate a denominator from that. Which is equal to the squared magnitude of direction 1 times the squared magnitude of direction 2 minus the dot product of the distances, or rather the dot product between the two axes squared actually. So that means the distance between the axis product. So we now know how big the difference is between the It's all right. Good luck, man. Thanks for dropping by. Or rather, the dot product in regards to the, and now we have a value we can check if the lines are parallel. If it's lower than um, um, then we want to simply use either one. Let's see if this is larger than 2. We will use the, otherwise we will use h2. Let's see. And we should probably return here eventually. Maybe we want to split this off into a different function. I mean, we want to be able to return if we end up in a situation with an error. Like this is actually a situation where the lines are parallel and we will just use from the collision detection whatever is relevant. We could do an inline function. If we wanted to. Maybe that would be better. Anyway, let's see. Nah, we can do we do set our contact point here. If we're in this situation, we set it to 1. Whoops, that's not the right one. point on H1, and otherwise we do it on, whoops, on points on H2. Yeah, we don't need to jump out of this function. This will only get called if the lines are in fact, or excuse me, parallel. So yeah, then we do a multiplication. Let's see. Let's see. Multiplier 1. Oops. The dot product of 1, 2. Let's see. The directions. The dot product of the directions with the dot product of position 2 minus the squared magnitude times the dot product of the difference in position 2 divided by the denominator. And we have the squared magnitude of direction 1 here. And that is the same. We have that. And there we go. If the multiplier for 1 is greater than the OBB axis, not axis, but the half widths of 1. Wait a minute. I'm doing this wrong. There we go. So if that's the case, or it's lower than the minus of this, or if the multiplier for number 2 is higher than, let's see, ABB, and we do axis number 2 here, or that is lower than minus this, then we would be out of bounds, and we would do the exact same thing here. Otherwise, we will create a point, center of point 1 is equal to math vector scalar scaled vector vec3 at scale 3. So we take the point of 1 and add the direction of 1, which is the axis here, and we simply add the multiply here of 1, and we of course need to get the axis of 2, and multiply with the, and then we want half of those combined. So contact point will be math add math scalar 0.5f, and we will do the same with this is 2 actually. There we go. All right, this should be the calculation of our edges, meaning that whenever we have edge collisions, we also get a nice contact point. Let's just disable the generalized debugging and move it inside here. Yeah. Well, something's not right because these values are not great. I mean, no, we do not get any information there. I mean, or maybe they are fine. No, they're not fine. They're definitely wrong. I mean, look at the point values. They aren't making any sense. Let's see, the contact normal, does that at least get calculated correctly? The contact normal. Let's see. No, the contact normal doesn't seem right. Let's swap that. Let's see. So no, that didn't help. Yeah, the contact normal definitely isn't correct. I mean, positive x is that way. Yeah, so that's the first problem. The contact normal is not correct for this calculation. Yeah, so how do we solve that? If we disable this, what will happen to our calculation? Let's see. Our contact normal is still not correct at all. Let's see. I want the console a bit on the other screen so I can see it. Well, there we got something close to a real contact normal. Wait a minute. This is probably wrong as well. That looked more. Some of it looked right. It's definitely not right per se. If I just could. get the contact normal to be the correct direction. Let's see. Huh. We're a bit in trouble here. Or rather, I am. Let's just see what debug information I get over here. For some reason, the contact normal is completely wrong there as well. Ah. Oh, wait a minute. Yeah, I actually have to do something else here as well. Because we have to cut out the components that are not needed before we do the transformation. Otherwise, we end up with information in our edges that are not correct, and then the dot products will be different. So this is actually also a mistake. We're getting closer. We're getting a lot closer. Still not there, but still not there at all. But Let's just try doing that. Maybe I'm getting too hung up over the contact normal stuff because I mean, the contact normal there is pretty fine, I think. And now it's, for some reason, I think, completely fine. I guess it depends on the, yeah, I don't know. But the Y component of stuff, or rather the C component of the stuff is way too high. The contact normal is actually almost correct. Maybe it's when I have too deep a interpenetration. Yeah, maybe it's just that. Hmm. Maybe I should try swapping the smaller than and larger than signs. Hmm. Do we want to flip these? Flip these. There we go. Yeah, I said I wanted to use... Yeah, this is wrong. I also said I wanted to use the dot product of the two axes. Let's see. Ah, whoops. I ended up pausing the physics simulation. That does look somewhat better, doesn't it? Minus 15. Yeah, that looks a lot better. That actually looks somewhat correct. Great stuff, great stuff, great stuff. So that's the error. I think I'll just go through the code once more, or rather the last part here. And then we have the multiplier here, which is the dot product of the directions. Position 2 minus the squared magnitude of number 2. And then we have the squared magnitude of 1, and it's dot product of the difference in positions number 2 minus the dot product of the directions times the dot product of difference in position 2. And we check the multipliers if it's greater than the size of the first axis or lower than the negative axis of the first. Yeah. I think this is correct. Hooray! 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 Finally! I think this YouTube series part has been one of the longest, and as you can see here, we get a contact normal that points along the x-axis. The contact point is somewhere over here along the negative x-axis, along the positive y-axis, and a bit along the negative z-axis, which looks entirely correct. Oh, that's great. Now we can do actual physics manipulations. Great stuff. So the last thing I will add to this method is a way to pass out the contact normal and the contact point. So we will pass out a vector contact, let's see, out contact normals, and then out contact points. And we will use that method. And we will simply store them here for now, even though contact normals, even though we want to pass them out. Contact points, normals, points. We simply disable this, and then for whatever calculation, we will store it. So out contact normals, place back normal, out contact points, and place back contact point. Great stuff. So this is simply a combined OBB on ABB separating axis test with contact point calculations. It handles point on face in the first 6 axis comparisons if the smallest penetration is along one of the faces of each box. So first, if it's on the OBB faces, that there's a penetration of the ABB, which is highly unlikely here, but we do have it for future use in case we decided to move an ABB or AABB. And this checks if we have a contact point on one of the faces of the OBB, as I've mentioned, and calculates where the contact point is. The next part is if we have a contact point from the OBB on the AABB faces. We calculate where the contact point is, and of course, for every calculation, we do the contact normal. Yeah, down here, if we have two edges that collide, or rather, the separating axis is a part of a cross product between the or rather, you grab the separating axis, which are not some of the base axis of either object. We must have some edges that are colliding, and therefore we do calculations on what point on each edge we should use as our contact point. And yeah. The next thing we could actually do is some sort of clipping. I would like to implement a part of the physics system that is able to take at least one contact point and correct the object motion from that. Even though in order to do what is called resting contacts, we would need a system that compiles several contact points over time for different objects. So yeah. We'd want that eventually, but right now, we do have a start of a system, the start of a system that will check for, or rather grab the correct information out of the collisions. Yeah. Also, I think I need a bit of a break in terms of calculating different contact points. I've been going at this all day. As I've mentioned in the start of the video, I even implemented a GJK method that works with simplex calculations. It works perfectly in terms of collision checking, and as long as you do the support methods, then you would be able to simply use this method for any polygon. Yeah. So I started working on the SAT version this morning. Then I wanted to swap over to the GJK, and I implemented that and realized that working out contact information would probably be a bit slower to do with that method, although now we have a starting point for implementing it. So I decided to revert back to the SAT method, which, as I started the episode by talking about, the first version I implemented was kind of broken. These are down here, since they do not handle parallel or close to parallel access very nicely. This method does checks for that inside this method here. So yeah, it's more robust, and it's also somewhat more understandable. Whether it's faster, I don't know. Speed is not really a concern right now. Anyway, we finally realized what I had as a goal for this part of the episode. Eventually we could do something like this. where we find by clipping with different planes, we find the actual contact information for whatever intersection yeah, as this article mentions, you could do caching as what I for now plan to do at least. I might implement the clipping method eventually, but we will do some caching of the contact points for each object. Yeah, and check that out. Then we will probably implement a method over time that does the clipping stuff to see whatever works better. Anyway, this combined SAT and contact information derivation is quite nice. So we have an early out if the objects don't penetrate. Otherwise, since we're at it and have the information at hand, we just simply calculate the contact normal and the contact points. All right, great. So okay, one last step. We do move the out contact normals and out contact points. Let's do this. We comment out the old version, add a semicolon. We move this outside of the method and put it right there. And then we pass in the out contact normals and out contact points. There we go. And now our method compiles. Not only what collisions we have between our one dynamic object. Of course, we need a more generalized method eventually, but once you can start getting a lot of different objects, you would want space partitioning anyway. So yeah, for now we play around with our one objects. Yeah, so that is it. Let's see, everything should compile. And that it does. Great stuff. All right. I definitely need a break. Gotta get some food. Do some stuff. I'll probably be back later. But thanks for watching along. You endured a lot. If you watched any of this in the future or just stuck around today, a lot of different math. Yeah, but it ended up working out. Well, it ended up working out in the end. All right, I'll be back later. Feel free to comment, like, or subscribe. Follow on Twitch or YouTube. Hopefully, I'll be seeing you.